Hey everyone, we'll get started here. As people trickle in, we can go back and forth here. Let me move this a bit. Alright, if you can hear me, and if the audio is loud enough, just kind of say something in chat. That would be nice. We're gonna do a little bit of where we're at and where we're going. So I'm recording the lectures live that I would be assigning next week. We were scheduled to come in Tuesday, have a lecture, and have an exam today if we would have been in class. Now, because all lectures have been postponed until next week, what I am doing is I'm recording the lectures with the ability for people to come in live. These lectures would have been assigned online and then in probably in smaller little bites. But I've been noticing with the few that I've been doing already that the interaction is helping focus them a little bit better. So all due dates are going to be adjusted. We're going to have an online exam for Chapter 3 that will be due by the end of next week. So that'll be Sunday at midnight, and you can take it at any point in the time next week. I'll open that up Friday. I will also put up a practice version that is similar to the worksheets I handed out to you, but that practice version will be like the online, so you can get used to the format. You can take that as many times as you want, just to get comfortable with it. Then in all the homeworks and all the due dates will be like homework before. For the in-class work that we did, I'm going to turn those into quizzes. So for any examples, now I know our particular class, because of the snow days, the in-class stuff wasn't being done as much as possible. We lost 2 days with the snow days, and so I kind of squeezed a little more lecture time out of the classes, which got rid of some of the in-class stuff. We have done some of the worksheets, but I'll be doing those as quizzes in Pearson for the points on that. Phoebe, can you hear me? Since you said hello in there, I just want to make sure the audio is coming through. Otherwise, that would have been like a very useless intro. And so I'll type that in there and see if I get any response. Because I know the audio was a little lower last time, and I readjusted the microphone levels and pulled the microphone closer. So hopefully that will all work out. And I'm going to actually wait on that before beginning. So much of today is going to be talking about sections 4.1 and 4.2 in the book. We're really going to be working on 4.1 and 4.3 over the course of the lectures while we're wrapping up Chapter 3. This is exactly like what this week would have been, just in this new format. Let's see here. I've got a good connection. It's showing audio on my end. Let me just double check over here. Oh, thank you, Jasmine. And I'll just write in here. Sorry about this. I just want to make sure that we have. I want to make sure that we have good stuff. Otherwise, just standing here and doing things for and about 50 minutes or an hour would be kind of pointless. So, if you hear a little bump, I just move the microphone a little bit closer. All right. Well, then I'm going to get started discussing Chapter 4, working our way through the ideas that we have with that. And yep, I can see you while I have the blackboard up here, so I'm going to scroll this up here. And what we're working with is polynomials. And polynomials means many named pieces. And specifically, we're going to look at functions in this really ugly form. And let me write all this in here. Makes it all the way through. Yep. All right, I'm going to explain what my crazy handwriting looks like on this blackboard here. So these subscripts on a sub n minus 1, a sub 2, a sub 1, and a sub 0 means that these can each be a different number. And so the a sub n's, I'll pluralize that, are constants. Some number. And the xn defines each term. And what we end up doing is we will name a polynomial by what we're going to call its degree. So the degree of a polynomial is n. It's the highest power. Now, we have already started working with functions that were polynomials. What we worked with was, I have f of x equals some constant, and for example, I'm going to put an actual number in, 3. This is a 0 degree polynomial. And it was a constant function. We also had, again, I'm going to use very specific ones instead of general forms here. This is a first degree polynomial. And it was a line. As I run out of room over there, I think I'll just put poly down for it and make sure this is still staying on the screen. Yeah. And then in the last thing, chapter 3, we worked with which, when we expand this out, looks like this, right? And this was our parabolas or our quadratics, and they're second degree polynomials. Just put a dot there. And I have been trying to warn you that we're going to start looking at things that are higher than second degree polynomials. Now, a lot of the tricks that we will use, we will break them down. We can make them built out of first degree polynomials, linear factors, and second degree polynomials, quadratic factors. So our game will be division and factoring as we get there, but I want to talk about the things that we're going to play with and what they look like. So we want to kind of get used to the definitions of polynomials and what they look like. So this is what we've seen before, and I'm talking about them as if they're polynomials, looking at the power of x. So here the power of x is 0. Here the power of x is 1. And here the power of x is 2. And this is the preferred way of writing it. We write the highest power of x out front with its coefficient in front of it, and we decrease the power of x until we get to the lone constant on the end. This form here, let me highlight it. We really like because we can see the vertice there. And that form is for our kind of geometric understanding. But in general, when we write polynomials, especially higher order polynomials, we won't get as clear-cut geometric things out of it. We'll want to focus on this idea of descending order. And so notice how the power of x, the power, gets smaller for each term until we're just left with the constant at the end. So let's look at a third degree polynomial. So a third degree polynomial. Sometimes you'll hear these called cubic because cubing is taking things to the third power. But what we want to do here is just look at the form that we would write this in. So we would have f of x equals 12x cubed minus 3x squared plus x minus 1. Again, what we're doing with the polynomial form is the powers of x decrease, and we put the coefficients out front. We end with a constant, and in the notation of a polynomial, this is the a sub 0 term. So I could say a sub 0, the constant with no variable term, is equal to negative 1. A sub 3, the constant in the front, is 12. And we'll find that these two numbers are very important for us. The leading coefficient, this is, and the constant. Now the leading coefficient, the subscript number, will change it. It will be related to the degree of the polynomial. And so as the polynomial increases, the leading coefficient will increase also. So let me pull a different polynomial here, and we'll look at the leading coefficient and the constant on it. So sorry if you hear my mouse bouncing about as I switch between screens there. So we'll say k of x just to have something different. And then I'm going to move my book here if you hear some thumping. Sorry about it. I just want to be able to see everything between my notes and the book. All right, so we're going to have negative 1/2 x to the 6th plus 4x to the 4th plus x. Now this polynomial, because the highest power is 6, this is a degree 6 polynomial. The leading coefficient will be a sub 6, and it will have the value of negative 1/2. And so that's the leading coefficient. But wait, this is x to the 1st power, and so if I scroll back up, a to the 1st power has, or x to the 1st power has my a sub 1 on it. I don't have anything without the x variable in it. So what number do we use when we don't have anything? Right? We use a 0. And so the constant is 0 in this case. And so this is the form we're looking at, and some of the terms we're going to focus on directly. Leading coefficient. I remember to put my T in there, right? That's almost English sense. My leading coefficient and the constant. And so the number up front and the number without a variable. Now, sometimes that can vanish if it's 0. Right? Zeros and ones are odd things, right? I guess I'll do a... Oops, let me change color here. I'll do a J of T. Just a... I like using functions of different forms, not always x, even though a lot of the things we do will use x as our independent variable and f as our dependent function naming. but I like to do them differently just so we know that these things are flexible. In this case, all right, we do write the constant of 1 as a constant because we need to see something there. But here, the leading coefficient, a sub 4, is 1, right? And so those two special numbers, 0 and 1, which we use to build every other number and every other little identity that we use in mathematics, they're going to sometimes be invisible for us. And so we just have to pay attention to that. And so here, so here, right where we have no constant, we could say, I think I'll do this in orange so it stands out as an addendum, that the constant is hiding there as plus 0, which is why I was able to say this. Well, here, I can say I can multiply this by 1, because it doesn't change anything, which is why I can say the leading coefficient is 1. And those are things we have to pay attention to. Ones and zeros, because of the identity properties, mathematicians tend not to write them, though they're hiding in the background. So I just want to point that out as we go through and look at what we can do with our polynomials, right? Those ones and zeros are going to hide behind everything. All right, so polynomials appear in different ways, and their appearances, or at least graphically, kind of get influenced, not kind of, or is definitely influenced by the degree that they are. Now, depending on how dramatic their coefficients are, sometimes you don't see every possible manifestation of the degree. But what I'm going to do here is I'm going to switch over to two examples in the book and give an explanation of what parts of a polynomial are. We're going to look at the parabola, which we use for quadratics, and we're going to really talk about that idea of the vertex. And I know I've been previewing this as we worked our way through. I've put up a couple graphs and tried to kind of hint that the things from the parabola would appear back. But this example in the book, I think, would be a good place to start. So let me switch over to here. And here we have two functions. We have a parabola, and in fact, due to the nature of knowing the vertex and having a point here, we could actually figure out the equation of this. I'm not going to go through that right now, but I want to focus on visually the things that we have with a parabola. Now, I said the vertex itself becomes a minimum or a maximum. And so minimum and maximum get this word extrema. It means the extreme positions, right? The extrema are places on a function where the values are extreme. They're either the most or the less, minimum or maximum. And with parabolas, the vertex was either going to be a min or a max because the function was stuck with that value as its starting place going up or down. And so this has an absolute minimum. You cannot get any smaller than -6. But because there's no other stopping to this function, it continues off to infinity, there are no absolute maximums. You can always get a larger number, increase x or decrease x, and this function will continue to grow. So it has no absolute maximum. Now we're going to compare this to this polynomial. Now this polynomial, I'm going to just note here, has 1, 2, 3 bumps. This had 1 bump. This was a degree 2. Let's see if I can write on that. Let's see here. I'm trying to see if I can. Yeah. So I'm trying to pencil here. It's let me. Oops. That's the one thing I don't like about. Nope, my pencil tool is not working too well here. So we'll make a note here. This is degree 2. 1 minima or maxima, 1 extrema for degree 2. This has 1, 2, 3 extrema, so this is a degree 4 polynomial, at least. It could be a higher degree, sharing minimums and maximums between the degrees. But in general, the number of degrees of your polynomial, you will have 1 less extrema. So this is a degree 2, I've got 1 extrema. This is at least a degree 4, I have 1, 2, 3 extrema. Now this here, point C, is an absolute maximum. The function never gets any higher than 12.7. So absolute mins and max limit the whole function. No matter what value you put in, you'll never get bigger than that. But notice it continues off towards negative infinity. So there is no absolute minimums. You can always get smaller. But in the middle here, there's this turning point. And we call that a local minimum. Because if you're near this point, the function is okay. All right, so I'm going to go back and look at the slide and see if the mouse shows up. So when I click on it here, just give me a second, my mouse should show like a hand there. Can you see that moving? Oh, no, it goes away. Okay. No, wait, there it came back. Yeah. So can you see the mouse move? I just, it's coming across on my YouTube where I'm watching the output of this. So let me try to get the highlighter to work so I can use the highlighter. All right, so it vanishes when it hits the graph. Okay. Thank you for that, Alex and Kiona. No, I see what you're saying. It vanishes when I hit the graph here. So let's go here. You see the arrow out here. When I go over here, it turns into a hand, but the hand does not show up on the feed. So let me fix that. And then I'll go back and talk about, see, I see. Okay, let's look here. All right, give me 1 second here as I move this graph about. Thank you for pointing that out. This is why I don't like PowerPoints. In fact, that's what I'll do here. a little drawing here, and we'll come back. So right now, if we look at these two graphs, there are some letters labeled on the side for A, which talks about the lowest point on the parabola, B, which talks about the parabola going off to infinity, and then on C, we have the highest point on the quartic function. D, it goes off to infinity. F, which is a little local minima, and E, which is a little local maxima. Now, I've drawn by hand these really quick, and I'm going to go back and forth to that video, and I will find a way to move my graphs onto my drawing tool. So I'll work on that. So here is my representation of those two graphs, really quickly drawn. And I'm going to point to these, the same things as I was pointing at. So we said with quadratic functions that they had a min or a maximum. And in this case, I think this is at 2 comma negative 6. And we had, I think, there were 2 points here that we could have used to figure out what the exact function was. And so I'm kind of trying to repeat the things I was pointing out before that you couldn't see the pointer on. Because the function cannot get lower than the vertex is an absolute minimum or maximum. We'll say absolute extrema. And in this case, it's a minimum. It's an absolute minimum. The function never gets less than negative 6. It has no absolute maximum because it can always go out to infinity. So no absolute, I'll abbreviate it, maximum. Abbreviate the one, not the other, but there we go. I'm not saying that that's a rule. I'm just saying that's me being odd there. All right, and so for the quadratics that we were looking at, and the quadratics that we did in chapter 3, that vertex was the absolute min or max, depending on which way the function pointed. But when we have a higher degree function, it turns, it changes direction. So from here, this function is increasing. It reaches this turning point, starts decreasing. Reaches this turning point, starts increasing. Reaches this turning point and starts decreasing. And these turning points are extrema. This point here, which the previous graph says is negative 2, 12.7, is the largest place this function will ever be. And so this one is an absolute maximum. So I'm just going to put over here ABS max. Because the function never gets bigger than 12.7. Change color here. Off towards infinity, on either end, it can keep getting smaller and smaller, so it has no absolute minimum. You can always make a smaller value. But here, at this point, which I'm scribbling towards, we're going to call it a local minimum. If I'm near this point, that's the smallest value I can get. Get rid of some of my scribbles here. De-scribbling a bit. There we go. That's a local minimum. And so if you're in the neighborhood of this point, that's the smallest value you get. Remember, when we look at our functions, when we look at using the difference quotient when we look at approximating them linearly, we always talked about being near where values mattered for whatever the function was measuring. And there might be a case that this describes something, but we only care about in between these points because that's all we're going to measure, or all that matters. And so localization really talks about what things would look like if you're in a limited part of the domain. And over here, this extrema, or this turning point, is a local maximum. It's not as big as the maximum here, but if you're in this area, if you're near this, it's the highest value the function will get. Now, I know these definitions don't sound horribly mathematical, right? If you're near something, but as we work with functions, nearness will develop some mathematical definition. In fact, a lot of the idea between functions and the pre-calc work leads into how we can talk about being near something. Calculus specifically works with the idea of the change and increase and the change and decrease, and how you find these extremas. And so I'm going to switch back to their graph now that I pointed out the things that I wanted to. And thank you for pointing out that the pointer didn't work. And I will work on a way of dumping these images into the blackboard so that I can use my pointer there or get a pointer that works across here. So in these two functions, we can talk about absolutely talks about for every possible value of the function, it is either the absolute max or absolute min. And most functions will only have one absolute. They'll either have an absolute max or an absolute min. At the other direction, they will go off to infinity. There are other functions that have no absolute maxes, but they shoot towards negative infinity on one side and positive infinity on the other. But only locally do they have peaks. And we need to be able to discuss what happens locally if our inputs are only valid for a certain part of the domain. So to find extrema, we want to find out if they're max or min, and if they're local or absolute. Now, a function could have more than one. In this case, this function here has one absolute maximum. But notice that one absolute maximum is 11. So if you look at the number is in parentheses of the 2 points at the top of this function, they both peak to the same number. So you can only have one absolute maximum and one absolute minimum. That doesn't mean it doesn't repeat across the function. And this function is an example of that. And also this one is, so this has an absolute maximum of 11. And 11 is the red number in the parentheses there. It does not have an absolute minimum. It shoots off to negative infinity once it goes to either side of that. And so this is saying, hey, it is possible for that absolute extremum to be at two values of x. And those two values are the two parts of this hump. Kind of like, well, I always forgot what my camels were, which camel had two humps and which had one hump. This would be a two-humped camel, but the humps are the same size. Absolute maximums are also local. And local maximum minimums talk about when you're near the x value. And so we have to look at what we mean by being near and far. So here is the mathematical definitions. And we are starting to get into the part of mathematics where our definitions aren't formulae. And so I'm going to break down each part of these. So C is any x value in the domain of a function. Remember, functions don't have to be from negative infinity to positive infinity. There can be points where values don't exist. We can give different domains to functions. There are domain restrictions. So whatever the domain of the function is, there can be some point inside of that. If it's an absolute maximum, then in the value of that point is greater than or equal to every possible value for f of x. Notice this doesn't show us how to calculate it. It just says if that value at that point is greater than or equal to every other possible x value, then it's going to be an absolute maximum. And I'm actually going to point to that visually here. Draw this up here. Two seconds as I draw a quick freehand graph. All right, let me switch over to the graph. Okay, so this is some function, f of x. Right? I don't have a numerical value for it. And my domain is all real numbers. Right? And so my f of c here is I'm picking a point. I'm picking this point. And so out here is what my f of c value would be. So the idea that f of c is greater than or equal to f of x for all f of x means that if I plug in any value into my function, I'll move up and down over the function, and it will spit off f of x values. So I'll use this other maximum as an example. That's f of x, and I'm just going to say sub n. It's a particular x value. F sub n. And so this says if I have some point, f of c, and I plug in every possible value of x into my function, if f of c is always bigger or equal to any other values, then it is an absolute maximum. And so this is absolute maximum. And so it's a test. Notice we have to do the calculation some way, and that will depend on the type of function. All right, so this definition is generic. It'll work for every function, but then we have to find the tools for the functions we're looking at. And right now, most of those are going to be graphically. We will look for graphical features, and we'll tend to focus around these turning points locally. Right? We'll tend to focus around the local extrema so that we can get a picture of the whole function. Once we see it running out towards infinity, running out towards infinity, my loop didn't reach here. We know that hey, it's running off towards infinity now, and these are the points that we need to look at. And so a lot of that we're going to have to do graphically, which is why I kind of geared into the Desmos stuff before. We're going to want to plot these, and I'll do some stuff with the plotting as we continue. And so that's the definition for absolute maximum. I'm going to switch over here again. And hopefully now I'm on the second line here, where if it's an absolute minimum, well, it has to be the smallest value for the functions. And in the function I just drew, there is no possibility of it being an absolute minimum. So let me come back to here. Because these drop off towards negative infinity, if I were to compare any point on here to the rest of the function, if I went off towards negative infinity, right, f of x as I move towards, I'm just going to say I'm going to move towards, as x moves towards negative infinity, f of x keeps getting smaller. Right? So I keep going here. As I go off, this says, hey, this keeps getting lower and lower and lower. And we actually call this end behavior. The behavior that happens at the ends of a function. And big N behavior will sometimes happen, right? What happens as x gets towards infinity, negative infinity or positive infinity. And so this function has no absolute minimum because its big N behavior is to get smaller and smaller and smaller and smaller and smaller, down towards negative infinity. All right. Now, local minimums and local maximums are comparing f of c when it's near c. And near, for most cases, means until you get to the next extrema. And if it's going out towards infinity, then in the width of the extrema. So this idea of near, I hope you can see that, near, right? And near is what I want to look at in the function I drew. So we're comparing a point f of c and f of x when x is near c. So I'm going to come back here and we're going to look at this nearness. Let's see if I have a little more room on here. Draw my axis. And I'm actually going to draw a function that has no absolute minimum or maximum. And I'll show you why. So this function has 4 extrema. So it's a 5th power function. On this side, the function runs off towards negative infinity. So as x approaches negative infinity, f of x approaches negative infinity. Right? I keep getting x smaller and smaller off in this direction, and the value the function spits out gets smaller and smaller. Well, over here, f of x approaches infinity as x approaches infinity. And so the value of the function gets bigger and bigger the bigger my x gets. And again, that's the big N behavior, what's happening on the big end. So we can only talk about things being local. And so I'm going to use some orange here. I'm going to come down here. And I'm just going to call this C1. And so f of C1 is greater than or equal to f of x when x C2 is less than C2. Right? If I'm kind of near this point, and this is what the definition of near for an extrema is, I haven't reached my next extrema. I haven't made it over here. And at the same time, I'm greater than, well, an equal distance this way. So I'll come over this way, an equal distance. And in this case, we can say all of negative infinity, right? Because as negative infinity. And so this point is bigger than anything before it and until it gets to the next extrema. And that's what we mean by near. Notice it's not a formula. It's a visual description of what the numbers are doing. And that pattern in the numbers is valid. And so we start playing with the idea of near being how we define the local part of the domain. I tend to look at it actually as these points kind of halfway here. But that we'll learn more. For now, we can say, hey, this is the biggest thing until I get to the next extrema, right? And this is the biggest thing. Well, I'm starting off from negative infinity here, so this is a local max. Well, f of C2 is less than or equal to f of x for all x near C2. And I would actually say, hey, x is less than C3 and it's greater than C1. That gives us our locality there, and lets us know this is a minimum, because this is in between these two extrema, and it is the extreme minimum. Now there is a tendency for extremas to turn. This extrema is a local max. That means the next one's going to be a min, because when you work towards a maximum, you're increasing, and then you're decreasing. When you hit the next one, you're going to start increasing. That's what these things do. You change your direction of change, the rate of change, the difference quotient along this side will be getting bigger. The slope of the difference quotient along this side will be getting smaller. It'll be negative. And so this increasing and decreasing pattern changes with each of the extrema. What comes out of this are some patterns that we might see also. And what we want to talk about is going to be symmetry, and some patterns that come out. And so the first symmetry we're going to talk about is even symmetry. And this actually has to deal with what's the behavior of even-powered functions. And then what's the behavior of odd power functions. Now, not all functions have even or odd symmetry, but the big end behavior will be the same based on the power. And we're setting up definitions here that we'll then be putting in mathematically. So please, I know right now no formulas are popping out, but we're looking at the behavior of the functions we're going to be using. And so on this first graph here, this is our quadratic degree 2, and it has a minimum point. This function right now is symmetric to the y-axis, because any value to the left of the y-axis or to the right of the y-axis is exactly the same, no matter how far I go away. All of these functions, I could take the piece of paper and fold it in half. I could take this function and fold it in half around the y-axis, around this y-axis, and it would mirror each other. And so this is called even symmetry, and the functions that define even symmetry will be even functions. So take a second and see, just kind of visually, take these and fold them in half. Even if you have a paper copy of the book, you can watch folding over the y-axis. The function touches on either side. And we did some of that with the axis of symmetry in quadratic equations. We found the place that it mirrors over, which is defined by the vertex. In this case, that axis of symmetry is the y-axis. And so the graph is symmetric with respect to the y-axis. That's called an even function. Well, an even function has a mathematical thing. There's something we can do with this, and that's defined here. And so what I'm going to do is I'm going to pull this out. All right. And so even functions say that if I put the negative value in for f of x, if I put the negative value in for f of x, I get the same value I would have for x. And when I mean negative, it's opposite. So let's and this is testable. So I'm going to use our friend the function, and I'm going to call it so that we can denote the definition versus the particular function I'm looking at of x squared. And so this is the parabola that sits with its vertex at 0, 0, and is symmetric about the y-axis. So we know it meets the definition of an even function because we set it up to be that. But we're going to look at this test here. And so what this test is saying is if I take any value of x and its opposite, I should get the same value for the function. So I'm going to make a little table here of x, negative x, and f of x. Right, so we'll make a little table just to run our test here. And so if I look at 1, the opposite of 1 is negative 1. All right, so oops, I want to make my table slightly symmetric. Let me make my table slightly larger. There we go. So let me give a little more space. X, negative x, f of x, and f of negative x. There we go. That was the one I forgot on the end there. And so if I test the value of 1, the opposite of 1 is negative 1. Now if I put 1 into my function, right, so I'm dropping 1 into my function, so 1 goes into here, 1 squared is 1. Now if I put negative 1 into my function, negative 1 squared, well, negative times a negative is a positive, and that gives me 1. And I'll try with a couple other values, 2 and negative 2. So if I put 2 into my function, 2 squared is 4. If I put negative 2 into my function, negative 2 squared, a negative times negative is positive, negative 2 squared is also 4. And so notice these things are equal. I can also do it in reverse. I can say, hey, what if my value of x is negative 1? Well, the opposite of negative 1 is 1. If I put negative 1 into my function, I get 1. And if I put 1 into my function, I get 1. So note, this doesn't mean the negative value per se. Though, when we communicate about it, it's usually the easiest way to see it. And this symmetry in these values is really what even functions are describing. This whatever you do on the positive side is the same that you get on the negative side. Is what we want to describe with even functions. Well, if there's even functions, then we should get odd functions also. And this symmetry is mirror. I remember kind of doing this visually. And I'm going to take this here and graph it on the blackboard so I can talk about it. But notice the wording here is another type of, if the graph could rotate, the original graph would appear after a half turn. And so if I turn this, if I make it move, if I turn this, so if I'm turning it on the center, and I remember when I had to do this, I did it on a, so if I turn this in this direction, coming around, this top point here would rotate down, this top point here, the top arrow would rotate down to the bottom point, but we're turning about the origin. And so all of these graphics come through. The other way of looking at it is if I fold the paper around the y-axis and then unfold it down around the x-axis, the graph overlays of it over its top. Notice that double folding comes in. So let me try to draw this here. The way I had visualized this when I first had it in school is we would put the graph and we'd put a pin in the origin, and then you would take the piece of paper and you would rotate it 180 degrees. And if it looked exactly the same, that was odd symmetry. And I'm going to try to do that here. All right. Now, the function that was showing here as the basis of the odd function was f of x cubed. So this is f of x cubed. And so if I rotate this point, all the way around down to here, I put a pin in here and rotate this like a propeller, this point would come down here and this point would come up here, and it would still look the same. So that's visually what an even function should look like. I see it as if I fold the piece of paper around both axes. So if I fold this over to here, it's going to look like, I'm going to change my color here, sorry. Going to look like this, and this side folds back here. So if I fold it or mirror it around the y-axis, it looks like that. And that's my first fold. Then in my second fold, if I fold it across the x-axis, this mirrors up to here and would overlay on top of this, and this mirrors down to here and would overlay on top of this, and I get what I started. So notice in both of these symmetries, we're doing some type of manipulation and we get what we started. On the even function, we just folded it across the y-axis and we got what we started. In odd functions, there are two folds you have to do. That means our mathematical definition is going to have some doubling to it. And so let's look at the mathematical definition here. And so notice f of negative x equals negative f of x. Notice the opposite is synonymous to a fold. On the even function, it was f of negative x equals f of x. On an odd function, it's f of negative x equals negative f of x for every x on its domain. So let's look at that. I'm going to clear this screen here. take a second. I'm cleaning off the blackboard, right? This is when I get covered with chalk. In general, I miss getting covered with chalk. All my chalk's sitting in my office. Well, I don't even have a blackboard in the house. I've got to fix that. But that is a different aside. And this is me still drawing this through. All right. There we go. Okay, so the function I'm still going to look at here is going to be the f of x equals x cubed. And we're going to look at the definition of an odd function doing this. All right, so I'm going to put in my x value here, and I'm going to look at f of negative x and negative f of x. And because I'm going to have to compare x values here and here, so I think I'm going to look at 1, 2, and 3 on this side. So 1, 2, and 3. Which means if I drop 1 into my function, right, so f of 1 equals 1 cubed, which equals 1. And the negative of f of 1 equals negative 1. So that's going to be negative 1. All right, so here's my normal function, x cubed. Have 1. So I'm dropping 1 into my function, but I want the negative of that answer. So there's dropping 1 into the function, and there's the negative of that answer. And I put that here. Now I want to drop negative 1 into my function. So if I put negative 1, so I'll do that over here, equals negative 1 cubed, which equals negative 1. All right, so I'll do the same thing with 2. So f of 2 equals, 2 cubed is 8. The negative of f of 2 is negative 8. And if I drop in f of negative 2, I get negative 2 cubed, which is also negative 8. And I'll repeat. Right. 3 cubed is 27. So the negative of 27 is negative 27. And negative 3 cubed is negative 27. And so that's how this test for even and odd functions work. Oh, sorry, didn't mean to do that. And so we now have the beginning of our definitions for polynomials. And so we can identify even and odd functions based off of these mathematical tests. So we have this description of how things are moving and where their largest and smallest values are. And when we apply them to polynomial functions, we can now look at things that happen with even and odd functions. So if you have even powers, you're an even function. And if your odd powers are only odd powers and only even powers, then you're going to be an even or odd function. And that helps us work out what the behavior of the functions are going to be. And so we're going to use these definitions to look at the behavior of functions. All right, This has worked our way through section 4.1. I'm going to do the next video Tuesday on 4.2 and 4.3 because we're going to be working with graphing. And we had the Desmos thing there. So I'm going to be placing up the assignments. Again, everything will start being due next, as if the classes are next week. This is how I'm recording the lectures so that you can get your questions asked while coming through. It also helps me get some things like, hey, notice that the PowerPoint isn't pointing to things coming across, and B, I need to get a different graphing utility, right? And other things we'll work with because the virtual blackboard isn't the same, but we're really focusing on the definitions of polynomials. I will the review test I'm going to make live, probably take me about a half hour here, and so I'll get the review test up so you can practice it and get used to the test format online. If anyone has any questions, please let me know. Notice people dropping in and out here. Again, this records all the lectures. We can go back and look at them going through. Pearson is up to date right now, minus the in-class assignments and the test, which I'll be putting up there. Tuesday, I will definitely focus on 4.2 lecture-wise, and then I'll start assigning the lecture and the lecture material as we work our way through next week. So I'm just going to start ending the stream here and see if anyone has any questions. And I guess this is the polite way of talking while not having graphics go. Not my favorite visual. So I'm done. You can drop out as you go through, or you can put any questions that you might have into the chat coming across. If not, email me questions. All right. Well, otherwise, have a good one. Keep studying on chapter 3, and I will make that practice exam live, and then I will post the real exam to go through.